Economics is exciting, right? We have a lot to say, but you got to learn how to say it. And you got to say it in a controlled way, not just blah, blah, blah. Okay, I'll get started. Welcome back. It's lecture number 5, and we now move into the high gear of macroeconomics. So I really urge you to pay close attention to what I'm going to do today and next week, because it's extremely important. It's a new method, something very few of you have seen unless you're mathematicians, but I'm going to teach this in a cookbook way to teach you how growth economists, people who care about growth, the environment, the limits to growth, if you like, energy consumption, how they solve difficult models. Remember, economics is about feedback. The great thing about what we do is we actually think about what people do when they are stimulated by certain external events and how they react, and how this reaction actually feeds back on the original event. That's what makes economics so exciting. And macroeconomics is even more difficult because it's all from the bird's eye perspective. So today, I'm going to show you the analog of the Lagrange method in temporal models with macroeconomics and time. The key thing about macro is it's about time. It's not about a static situation, it's about a dynamic situation. And as you know, growth is about dynamics, and the first part of this course is about growth. So to understand the dynamics of a model, we need to think about how agents would do the best they can given the constraints they face. Okay, now remember last week I tried to motivate this with an appeal to a very interesting young person your age who was extremely smart and developed 3 or 4 very groundbreaking papers in his very short life before a lot of my students actually get their PhDs. He had already finished that. So it's an amazing person, and that's why we talk about the Ramsey model. We also talk about the Ramsey rule of optimal taxation. It's not a part of this course. It was part of Macro 2, if you remember. The Ramsey model is a benchmark for thinking about how economies should grow. And I motivated that last time because Ramsey himself was a bit troubled by the philosophical question of discounting, whether it makes sense to put less weight on the future and future generations' welfare. This is an extremely relevant point if you think about climate change and think about California right now. Okay? You know, we all think about Gottschalk's house burning down in Malibu, but think about his children and the children's children that may be living in California, what they have to deal with. And part of what Gottschalk has done today in his private behavior has affected the future outlook for his Malibu in 20 or 40 or 50, 60 years from now. So that's what the dynamics of, so if you don't like growth theory, you certainly might have an interest in economic management. And those of you who are thinking about economics and the microeconomics and macroeconomics of climate change, this is an exemplary way of dealing with it. And Nordhaus got the Nobel Prize for doing basically that. And if you're interested in that, please come to my lecture on the 5th of December in the Kapelle. Okay, unfortunately I have to do it in German because it's a German public relations deal. So if you don't, maybe you'll learn German before then, and you can handle it, or you can sit next to a German person who can give you an instantaneous translation. But this is really what all of growth is about, trying to understand the dynamic behavior, first of the optimal path. And that's why Ramsey is optimal. And everything else is kind of trying to get close to Ramsey. Okay, so, and one of the things we learn in economics is that there are externalities. There are reasons why the private economy doesn't make it. Okay, if we're honest economists, we have to deal with that. And that's what the message of the OLG model was last week, that there are shortcomings if the family does not think of not just itself, but future generations in the same way that it thinks about itself. There will be an externality on future generations. Okay, maybe we have too much saving, maybe not enough. And you can think of saving as a stand-in for things like environmental quality. Okay, you can think about optimal consumption of fixed resources and fixed supply. So all these things are kind of important. Unfortunately, in macro, even if it's an introduction, I cannot give you all the details, but some of you are clever enough, you could do it yourself. Now I could even give you a problem on the problem set where you actually have to apply this to something completely different. Okay, so think about that. All right, so today's outline, I'm going to go slowly. I'm going to repeat myself, which I don't tend to do often, because this is a very important idea. So I'm going to spend a fair amount of time repeating this, and then we're going to try to apply it. Then I'm going to show you how Ramsey's concept actually can be, under certain conditions, decentralized. We can apply it to a decentralized world where people are facing prices and deciding in possibly a selfish way, but under certain conditions, this selfishness actually gives us the first best. And that's kind of what we call the first and the second welfare theorems of economics. Okay, and again, you have to know why those theorems can fail before you can criticize them. That's what makes this field so exciting. Okay, so I'm going to remind you of what we did last time, trying to motivate Ramsey through the OLG backdoor. So the idea of Ramsey considering the welfare of all future generations, all future families. How would you somehow get that into a problem? Well, you could actually get into a problem if everyone were related. If your children had utility and you care about the utility, and you could influence that by giving a bequest, for example. Okay, so in some sense, we all have a chance of influencing the happiness of our offspring. Okay, maybe they've got too much, maybe we want to take something back. You know, that's also a possibility, but in general, we want to give them something, sort of committing them to a certain initial condition in their own optimal program. I tried to motivate that, and I urge you to go back to your notes and just look at the two-period problem. I've reposted the slides, and I will repost them again. There are little typos that keep coming up, and I'm grateful to the students who've actually gone out and tried to check this, okay? Because these things happen, okay? But the underlying result is there. Okay, and the question is, how do we understand that? Well, Ramsey, in 1928, in the published version, 1926, whenever he wrote the paper, was able to write down a problem back then using continuous time. So this is the limit of an OLG model with many periods. So we're taking an infinite number of periods, but actually an infinite dimensional problem in time. So it's like saying, okay, what are you going to do today? What are you going to do tomorrow at 9 o'clock or 9:10 or 9:11? So we have a continuous measurement of time. It's a theoretical construct. We cannot measure GDP continuously. We cannot measure even certain things like house prices continuously. It's just impossible. Okay, but we can still think about it. We have the freedom to imagine what that world would be like, and then we can try to distill the wisdom of the continuous time model to our everyday lives. That's kind of what Ramsey back in the 1920s was trying to do. So I'm going to write down that problem, continuous time. That's going to take a few minutes. And then I'm going to talk about how to maximize the welfare of a representative generation. Okay, so Ramsey's assuming that the government is basically doing this. I mean, I don't think he was a socialist, but he was thinking like a socialist. If I could do that and I could get everything right, what would be the best thing I could do for this household looking forward? Okay, so we can characterize that rule, but it's complicated because it's not just a two-period problem. It's a problem of controlling consumption continuously. Like you have your hand on a dial and you're changing the intensity of consumption continuously because you can, right? Or think about yourself driving down the Autobahn and you can accelerate or decelerate by putting your foot on the gas. That's kind of what this approach is like. It's like controlling a variable in continuous time. So we're not choosing values of a control variable in discrete terms anymore. We're actually choosing an optimal function. Okay, so write that down. A function. And you're masters. You should be able to understand this. So Ramsey's abstraction in the 1928 paper is to think about the choice of a function to characterize optimal behavior. So again, think of Nordhaus, think of the guys who think about environment. What is the optimal rate of pollution? Okay, it's not like a discrete thing, this quarter, that quarter. It's like in continuous time, how much do we want to pollute optimally? Can you say, oh, that doesn't make any sense? Well, it turns out that pollution is costly to reduce. So you can't spend all your resources to reduce pollution because maybe you won't have anything to eat. So at some points, there must be some sort of trade-off. That's what economics teaches us. Okay, so this very lengthy introduction is to get you excited about this because it's hard. Okay, and I never promised you a rose garden. You didn't have to come to Berlin, but now you're here sitting with me, and more people are showing up, which makes me very happy. Okay, and we're going to put the movies online soon, and you can watch them, but with a time delay. So it's like watching Babylon, right? And then maybe we'll take it offline for a while, which will incentivize you to come, just at least to take the notes, okay? This is really important stuff. I want you to learn this stuff. I'll be very happy if you do. So we're going to learn something like the Lagrange approach, but it's for this new dimension of problems that we're going to introduce. It's called the Hamiltonian, or the maximum principle. It's named after the Russian Pontryagin, okay? The maximum principle is a way to attack this optimal dynamic optimization problem. It's optimization of a function defined over a utility or a profit or some sort of number which is a function of your behavior of time. So you're not just choosing consumption today, you're actually consuming a plan for consumption over the rest of your life. Okay, and because of discounting, what happens in the future is not so important. It turns out that you can characterize this optimal behavior relatively easily using first-order conditions. So that's kind of the cheap way out is just to write down the first-order conditions that characterize optimal behavior. Now, a lot of you are saying, I'd like to see the actual rule. Then you need to make some assumptions. Assume a functional form, like the Cobb-Douglas function with Andreas, okay, or the log utility form. Okay, but that's kind of the second. You know how to do calculus. You can get to that step. The first step is to understand the abstraction. Okay, and what the first-order conditions for an optimal plan, an optimal function that solve the Ramsey problem have to fulfill. So that's the exciting thing about today's lecture and tomorrow's next week's lecture and the Übung tomorrow. You'll do this. So we're going to talk about the necessary conditions, like the first-order necessary conditions for a simple static problem or a problem in discrete time where you have a countable number of choices to make. Here we have a function, so it's like really choosing the plan of attack. And that's exactly how you should think of the optimality. It's an optimal policy given the state of the world that you inherit from the past. What is the best thing you do going forward? And that's how we're going to characterize it. So we're going to talk about a state variable and a co-state variable. State variable is the state of the world, and this simple model is just going to be the capital stock. And what is the control variable? How much do I consume at every point in time? Okay, so Ramsey's asking how much should a government or should the people directed by the government consume over time to make themselves in this particular way as happy as possible. Okay, so it's a really, by way of example, I'm going to show you this is a very interesting problem. If you go into this literature and the growth theory, take Professor Schwark's course in growth theory, and you'll get into this in more detail, okay, because there are lots of applications to this. But the Ramsey idea transcends that. The Ramsey idea says, suppose I could actually control everything, what would I do? Okay, that's already a very non-trivial problem. And then ask, okay, can a decentralized market, with or without a government, reach that optimum? And that's kind of a great characterization of what a lot of macroeconomics is about, understanding the failures of markets to reach some optimum. And to do that, we have again, this is kind of a cookbook method. I'm giving you the cookbook, and I'm going to actually say that on one of the slides. It's a cookbook approach. I'm just going to give you the rules. Just like when you do the Lagrange, you always think, okay, set up the Lagrange function, take the derivatives with respect to the variables and with respect to the Lagrange multiplier, set them equal to 0, and then solve it. Okay, that's kind of what we'll be doing here with a couple of extra twists. But you have to remember those rules, okay? You have to memorize them, commit them to memory, at least for the short term. Eventually it will depreciate and disappear, but to help you understand the world, you will remember that there are these ideas of conditioning your behavior on something that you've inherited from the past. That's kind of the basic idea of Ramsey. Okay, and we're going to use what's called a phase diagram. It's taken from physics actually, but it's actually very simple. It's going to describe a change of some variable as a function of its level and a level of another variable. So it's a very nice sort of visual, it's a visual. A lot of people like to work with equations and just with computers, but you need the visual to get the intuition of what's going on. And Ramsey's about consumption, a control variable, and capital, the state variable. Remember I told you about Angola after the war? They lost all their capital because of the Civil War. Okay, they had to start from scratch. And obviously they want to go somewhere because they are saving a lot. They're growing faster. So you can think of Angola as on a dynamic path to taking it to a better place. A lot of countries don't get there. So we're going to try to understand in the context of doing it right, What would be the right thing for the central planner in Angola to do, given the meager capital stock per capita that they're starting the game with in K0, K sub 0? Okay, so let's review last time. Let's remind ourselves what we did last time. We looked at the OLG world for the last time. We'll come back to it later. We talk about money, because the genius of Samuelson's OLG model was that you could use it to think about money. Remember, capital has value. And I'm old, I have capital from my youth that I saved, and I give it to the young people who are alive today and producing, and they give me food, right? That makes sense, but it doesn't have to have value. So Samuelson, even before Diamond, actually said, we could talk about paper money. This is a way of explaining how paper money works. As long as we all believe the money has value, fiat money can be used as a way of transferring savings between generations alive at any point in time. Genius, okay? And that is one way of thinking about cryptocurrencies. Okay, it's a great way of thinking about a lot of stuff that has no inherent value, but people still seem to value it. Now, if governments tend to print too much of the stuff, like in Venezuela, the stuff loses value. It doesn't have any value anymore. People don't accept it. You have a collapse. But it's kind of a confidence game. And the Samuelson model was the first formulation. Actually, Allais, the French guy, did it before, but he wrote in French and couldn't get it published in an American journal. But that's not a very good excuse. So the OLG role here is to have capital, a productive asset, being transferred from generation to generation. We can expand that to think about houses. You can think about money, you can think about gold, other assets, the environment. The quality of the environment is also is a state variable that's passed on between generations over time. But the genius of the OLG model was you have separate generations that decide separately and therefore have possibly external effects on each other, especially ones that haven't been born yet and can't bid in the market for environmental quality or for consumption. Okay? So we have this notion of dynamic efficiency and inefficiency, and we use that to think about how policy might affect the course of the economy. Maybe we can get better results by doing some policy, maybe taxing and transferring, maybe introducing a pay-as-you-go system, maybe the economy's saving too much, or maybe saving too little. And then I tried to motivate that by thinking about a person that lives forever. Okay, that's kind of ridiculous. But it's under very trivial conditions that Barrow identified is possible to see how generations, even though they're not connected directly, may decide in ways that affect each other's utility and may do that purposefully. Okay, so the last part of the last lecture, very important, was trying to show how you can motivate that using the assumption that people in the future behave the same way you do. And if that's the case, you should kind of think about that, because otherwise you're making a big mistake. You're not internalizing the fact that you can influence your children and your children's behavior. So then we talked about Frank Ramsey as a person who didn't actually write that model down, but thought about this long view. And we said that you can think about altruism as a way of motivating the Ramsey problem. A politician, okay, who is thinking about future generations, even though that politician may not have any children, is an altruistic person, a person who cares about the utility of future people and generations. So, spool back to Ramsey, think about this problem. But now we're going to use a different framework to think about it. Okay, we're going to think about a different framework. We're going to think about a continuum of time, which is exactly realistic. T equals 0, T equals 0.0001. Even between that, there's a little bit of time. So how does that change the nature of the problem, or does it change the nature of the problem at all? It changes the mathematics of the problem, but it doesn't change the intuition. So if you read Benassi's book, he actually takes the continuous time Ramsey problem and puts it back into a discrete time, just to remind you that it's all about economics. Okay, you can still get the intuition by playing with a discrete time model, but there's certain things you're going to miss. Okay, that's what we're going to try to get today. So Ramsey asked, how much should a nation save? Okay, this is a normative question. If you remember, the difference between normative and positive economics is very important. Normative involves a judgment. Okay, that's why it's should. Okay, you have to tell me what the nation wants. Maybe the nation wants something completely crazy, but maybe it actually wants to maximize the utility of its people. If that's the case, it's a normative question. The positive question was, how does an economy behave? under certain assumptions, under certain behavioral rules. Okay? Those are different things. They may coincide. They may somehow lead to the same outcome, but they're different questions. So we're now going to formulate this problem in continuous time. Okay, so this is a step for you, but you're masters. You came to this program because you don't mind using a little bit of math. We don't use that much math. Compared to my microeconomic colleagues, this is a kind of a cakewalk. Okay, and this cookbook cakewalk. Right? So we're going to use continuous time, take from the positive set of real numbers, and we're going to use that as an index. Okay, so that's the number, that's time. So we start in t0, t equals 2.5 means 2.5 periods into the future. Okay, and we're going to think about discounting like Ramsey did, even though he thought that was morally reprehensible. If you looked at the Ramsey article, one of the things he did actually say in English was that he thought it was kind of not so good to think about people in the future as being worth less than people today, or their welfare as being worth less. Not worthless, but worth less. Okay, it's all about relative. Economics is about relative. Okay, so we have this idea of discounting, and I'm going to use theta, as before, as some sort of social discount rate. It's the planner's relative weighting of utility using the exponential formulation. Okay, so it's Euler's constant raised to the minus theta times t. Theta is like a number like 0.02 or 0.01. Or, if you're environmentally very conscious, you might say 0.00001. Okay? So it's just a way of, and you can see as t gets bigger and bigger, that weight gets smaller and smaller, but at different rates. Okay, that's really, please understand that. You're masters. You guys are, when you finish this, you have a master's degree. So I want you to be masters of this universe. Okay? I say that every time I teach this course, and I really mean it, because I'm on the admissions committee. I actually see your applications. I know who you are. We're considering a government-less economy. So we make life easy for you. The government doesn't do anything. But Ramsey was asking the question, okay, what should a government do if the government can just give you the food and let you go, let you do your thing? Okay, so in a sense, government is everything. In the social planner's problem, it is everything. Later on, we'll ask whether the government could screw things up. Maybe the government could tax the wrong incentives and change people's behavior. Yes, it can. Okay, it may also do better things by supplying environmental quality or public goods like highways, mass transit, hospitals. Okay, so economics is exciting, right? We have a lot to say, but you got to learn how to say it. And you got to say it in a controlled way, not just blah, blah, blah. Okay? So, no overlapping generations. We're talking about a single family or a dynasty, if you like. And this dynasty may be increasing in size exogenously. Okay? So, again, going back to the beginning of the course, the solo model, exogenous growth of population, we're going to bring that back. People can't choose how much to reproduce. They can't let people in from abroad. It's just a simple, closed economy with no disconnection, okay? There are no new disconnected agents. Now, if you like this stuff, there's a whole literature out there about allowing people to come into such an economy. So the government may have an incentive to bring in people who are disconnected because they behave differently from the ones that were already here. Okay, this is not a message for any political party, but it's a very interesting problem because you have to think about that. And how much do you care about the people who are coming in from outside? Okay, because you have to think about that. And Ramsey didn't think about that because back then it wasn't an issue. Okay, so I can give you some references. One is Olivier Blanchard, and the other one is the 1985 paper in the Journal of Political Economy, and Philippe Veil, friend and colleague of mine from 1987. Okay, so let's think about the problem. Again, like the other problems we've thought about, you maximize an objective function. It's a number. I'm going to make that number as big as possible, but that number is no longer a simple sum of two utilities like in the OLG model. It's no longer a single objective function like the Phelps problem in the Solo model. It's a complicated problem because it's a function that we're choosing to maximize a number that sort of summarizes some of the aspects of that function. Okay, so how do we do that? We think of an integral. An integral is a way of adding things up. So we're going to add up a function in some special way. And we're thinking about utility. So how do you think about how happy you are? It's not just how happy you are right now, but maybe tonight or the next night or 2 weeks from now. How do we add those up? Okay, and do we want to smooth consumption or do we want to spread it? Some people used to think it was just a sum, just some consumption. My utility is the sum of everything that I've done over my lifetime. It's a bit simple, simplistic. Okay, so you might want to think of some sort of different way of weighting the consumption at different instances of time. So this approach is called dynamic optimization. It's also called, Ramsey called it, the calculus of variations. Okay, so there are many ways to skin this. If you're a mathematician, that's fine. You don't have to be one to be in this course. Okay, so there are many ways to attack this. We're still going to assume that agents have foresight, and this is one agent. It's the planner. So the planner is able to choose this, and he understands population growth is constant. He understands that all these other things are unchanged. All that can be altered. But for you, beginners in your voyage to become master, this is enough. Okay? This is what I want you to learn. The approach is called the Pontryagin's maximum principle. So like the Lagrange approach for the discrete choice problem, we now have a cookbook approach to asking about how to do this problem, how to make this representative household with sort of endless life. Again, thinking about maybe some sort of recursion is going on inside of that problem. But the household basically has this set of this utility over the future of consumption, and consumption is expressed as a function of time. Okay, well that's basically a simple problem if you understand the cookbook rules. And the cookbook rules basically say, I have to identify the state variables of the problem. Okay, what can I not change at any instant in time? Just like in the solo model, the capital stock is a state variable. I'd love to have a bigger school here. I'd love to have 3 of these lecture halls. But if I want to get there, I have to invest many, many periods. So I have to accept what I have. That's the state variable. And the control variable, in this case, it'll be called the co-state variable, is my way of getting there. Okay, so the control variable is a flow that's going to eventually accumulate to affect the state. Okay, that's the magic of this approach. And again, think about the environment. I love to, this is not a course about that, but you can see the examples are seething coming out of this problem, because you cannot change global warming from one day to the next. We're on a trajectory now. The state of the economy, just like the state of the environment. Okay, if you want to change it, we're going to have to work at it for many, many years, possibly decades. So it's the same logic with respect to the Ramsey model. What are the state variables? What do I have to accept at a point in time, and what can I control by changing my behavior between now and the next period? So think of this as they're all functions of time. Some things we can affect, and some things we have to accept. They're the result of cumulative action in the past. Okay? We also need to know where we started. The initial condition is very important. So if you start off like Angola, tough cookies. If you start off in the condition of Germany or Switzerland, you have a different starting condition. It's a different problem. So the initial conditions are incredibly important for conditioning and behavior. You'd expect that people in Switzerland would consume more than people in Angola. Okay? Not just because they have less, but also they want to get somewhere. That's exactly what the optimal policy will talk about. Enough words. Now we have to do some math. Okay? So I'd urge you to write down. If you just take some notes, you'll get the slides today, and you can actually corroborate, and then you can go and look in Benassi or in other readings and come to the section tomorrow. Okay? So we have a continuous time index. Okay? Little t. Don't forget that. Subscript t is shorthand for the value of the variable in date t. And some textbooks, like Romer's textbook, they use parentheses and t in the parentheses. If you can do that, it's a function of t, of course, but it tends to take up lots of space on the slide. Okay, so we use the shortcut of a subscript. In your head, you should think of function of t. And that's what you can choose, okay, if it's not a state variable. Okay, so Some things are exogenous, and you can't change those either. One of those is population. So just like before in the solo model, the population of the economy is LT, and it's given by an initial condition L0, and L is growing at a constant rate, little n. Okay? So what you see there is basically the solution to a differential equation, which is dl dt is equal to n times L. dl dt is equal to n times L. And dl dt is the same thing as L dot. The dot is shorthand for the change absolute with respect to time. Okay? So L dot divided by L is the growth rate of the population. Okay? So again, shorthand helps us. We don't have to write lots of stuff on the blackboard. Don't have to write stuff on the slide. Don't have to write stuff on a piece of paper. Okay? But LT is basically governed by this law of motion, as Andreas calls it. And the rate of change of L is a simple constant times the stock. The rate of change is a constant, and the absolute change of L is a constant times the stock. Okay, so it's the simplest differential equation you can imagine. Capital accumulation, we already talked about that. The central planner gets to steer that. That's the whole game. Okay. Remember the solo model, it was just a function of savings. Now this intelligent central planner is going to choose the savings rate. He doesn't have to look at anything, he just does it. He's going to maximize something. So think of solo as a cheap shot at Ramsey. Okay, Solo actually knew about Ramsey, but you didn't want to go, it was a hard problem, and he wasn't going to get that published. But he thought, constant savings rate, that might get published. I hope he's not watching this video someday. Hey, Bob. So this is an improvement. Ramsey going back in time is an improvement on Solo, because we're going to actually try to explain the savings rate. The savings rate doesn't have to be constant. Okay? So Ramsey in his wisdom is saying, okay, what should we do here? Let me just write down what happens to the capital stock. Capital stock, absolute terms, okay, that's capital K, not per capita, capital K is changing absolutely as a function of how much I don't consume and how much I don't need to replace the stuff I burned up. Okay, so that is also a differential equation. K dot equals Y, my output. The central planner may have some way to control that by controlling K, but K is a state variable. So how can the central planner control K? By changing K dot for a while. Okay, so if you change K dot for many periods, K will grow. As we learned that from the solo model. And if you do the miracle von der Substanz leben, then K shrinks. Okay? Again, this is the absolute level, not the per capita. We're going to get there. Yes? The E squared times? You mean here, this up here? I just inserted, just substitution, okay? Again, I'm doing this very pedantically, so maybe it's just too easy for you, but just to remind everybody that we have something that's changing, even though we take a snapshot of it, it's LT, but it's still growing. So if I take two snapshots, I get growth, okay? It's exogenous growth. The interesting stuff is K dot. Now, K dot is useful to us, and it's useful to the central planner because he's going to use the K to produce the Y, which makes us happy because we can consume it. And we don't want to consume too much. We also don't want to invest too much. So that's the whole magic of this problem. What is the right choice of my savings rate? And we're going to derive that from this differential equation because that's the crux. Okay, so the Y doesn't come from heaven. It doesn't come from like manna from heaven. It actually has to be produced. And the central planner can work hard to get bigger K or smaller K and affect Y. And we also have labor. And labor, I'm going to make life easy for you. Ramsey made it easy for me. Labor's constant. So people are just working, just like in solo. Okay, so it's just a simple, you can change everything. It just gets harder. And later on in the course, we will change it. We'll let labor become endogenous. You can choose to work hard or less hard. Presumably when you get rich, you want to work less. Okay, but right now, labor supply, exogenous, and the central planner just puts the people into the factories, and he creates capital by making people abstain from consumption. Okay, and that's this part, right? So YT minus the necessary depreciation to keep K constant will be basically that which is available, the net product, and if he doesn't tell or she doesn't tell the people to consume it, it will be saved and invested. Okay? Now I'm going to make life easy for you. If you're interested, David Romer has a great textbook, not Paul Romer, but David Romer, another Romer economist at Berkeley. He has a great textbook, which I don't assign, but if you like, there's a nice exposition of this. I'm going to set A equals 1. Okay, and maybe Andreas will give you a problem in the problem set, or just we'll take you through the example. To deal with that problem, you have to make more assumptions. Okay, so this is a fairly general setup. A is equal to 1, so there's no technical progress. So we have a static production technology, and it's still an interesting problem. Because if you're Angola, you got to get there. How fast do you get there? If you tell everybody to starve today, then they're not going to be happy. Okay, and if you wait too long, then people aren't going to be happy either. So it's kind of a trade-off. Okay, now this production function we normalize just like we did with the solo model. So we're going to divide everything by L, and we get the so-called intensive form. Okay, so I want to basically massage this equation to get the same intensive production function that we had last time. Okay, I'll do that in a second. It's easy. You know how to do that. All right, we did that already. You just have to ask, what is little k dot? Little k dot is a race between big K and big L, right? And big L is kind of trudging along at rate N, and k dot, you can accelerate or decelerate, and that's what the planner gets to choose. I'm trying to make it entertaining. It gets worse. Okay, so why does the planner care about this? Well, the planner wants to weight the consumption possibilities for her people. I like to use the feminine for the planner. Makes a lot of sense to me. Okay, so I'm going to, again, taking Ramsey really literally, I'm going to take separable utility. So what I consume this period is going to give me utility, but that utility is independent of successive choices of consumption. Okay, so people are a little bit like robots in this model. They don't have any sort of habit, but you can put that in there too. You can put all sorts of stuff in this model. It's the basic stuff that you're learning today. Okay, so this integral is the sum of all the utility that my household that I'm trying to make as happy as possible, okay, living forever. How do I do that? Well, the household evaluates utility with a utility function, which has a positive first derivative. Okay, and this is consumption per capita. Okay, so it's little c. And then the curvature of the utility function is such that it has a second derivative that's negative, so it's concave. Okay, that means that people like you and I like to smooth consumption over time. We don't like to go from 0 to 100. We like to take it easy. I mean, slowly, right? If I'm going to get rich over time, I'd like to sort of get there, and then I don't have to have these big jumps in my consumption to make me uneasy. That's what this utility function is trying to capture. Okay? So the integral is simply just a sum. It's just a fancy sum. It's the sum over every instant of time. Okay, this function, which doesn't change, so even though I'm older, I still have the same valuation and the same type of valuation of consumption per capita. And then I discount it using the social discount rate because my social planner, she's doing it for me. And later on, we'll do the private solution. And we'll see how that looks. Because the private solution may have the private guy faces an interest rate and has to borrow and lend to do the right thing. But the social planner can do whatever she wants. Okay? So think about that. You can also think about, Jeremy Bentham thought about people's utility. He took it very seriously. A lot of us don't take it that seriously. He thought you could actually, it's like sticking your finger in a socket and you get an electrical shock. It can be an intensive shock or a less intensive shock. Don't try this. But the idea was Bentham thought we could add these things together. So I could take your utility and just add it to mine, and then we could get lots more utility. Okay, so if you take that approach, you might just say, okay, let's have a different discount rate, call it rho, and weight everyone's utility by the population size. Okay, and remember, n is growing, and n is L, same thing. I'm just using n because you might think of people actually not working, but in the end, they're all working. Okay, so if you take the solution to the equation we had before with L, okay, it's just the initial condition blown up by growth rate n as exponent to Euler's number times t, and that hits the utility. Okay, so if you do that, you could just write it like this. So you can see that's the same form as this one, just a different weighting of people. Okay, so you know, again, the Ramsey question arises again. What is the right theta? Okay, but now we're just saying, okay, if you care about people instead of generations, you'd want to take the social discount rate for utility, and you'd want to net out the fact that you have population growth. Okay, so if population is growing, you want to put more weight on the future because there are more people out there. So the correct discount rate will be a bit smaller. Ramsey said it should be 0. He said you should weight everybody the same. Okay, but then you have a problem with the utility function. Okay, if theta is equal to 0, that sum is not defined, it's infinite. Okay, so there's some interesting problems. So we need to have some discounting to make sense, and he understood that, he just didn't think it was very moral. So it's kind of like the tension the economists feel when they go to bed at night. How should I feel about this? And actually, if you're really interested in this, the environmental discussion is very relevant here, because Nordhaus and Nick Stern, these are people who think very deeply about environmental policy and global warming. What discount rate should we apply? Thinking about global warming, we should have a very low discount rate. Okay, so again, it's the same issue. But we're going to take theta as being positive, so we will have discounting. It'll be much smaller than if we just consider the generations with population growth. Okay, so that's the one we're going to use. So now I'm going to go back to the idea of what Ramsey was about. Ramsey said, okay, I'm the social planner. I'm going to try to make that thing as big as possible. I'm going to try to make that's a number. Okay, this thing is a number. It's an integral of a function. Okay, it's an integral of a function of a function. Think about it. It's a little bit complicated, but the u doesn't change. CT can change over time, and I'm choosing the whole thing. I'm not just choosing CT in period 500 or 50 or 5. I'm actually choosing the whole thing, and it has to be consistent. And that's why Ramsey was so important in 1928, because he actually, or 27, he put his finger on this. Okay, he said these are not disconnected decisions. If I save a lot today, I'm going to have more possibly to eat tomorrow. But if I don't save enough today, I'm going to have nothing tomorrow. So I constrain myself. You have a resource constraint. But it's not a single resource constraint. It's a set of resource constraints. It's a continuum of resource constraints. Every period I have to obey that what I have to eat has to be a function of what I've produced and what I've got left over after I've depreciated my capital. Okay, so this is extremely deep, and people had problems handling it, I think, back then. But you know, it's a long time ago. We've come a long way. So here's the problem. I'm going to maximize. She's going to maximize this sum choosing a function. So it's not just a single value of c. It's ct for t equals 0 to infinity. Okay, and it turns out under fairly mild conditions that it's going to be a continuous function. It's going to be a function that we can differentiate and things like that. Okay, it's a function. It's an outcome of the setup we have. We don't have any jumps in the valuation of consumption, so we're not going to have any jumps in the choice of the optimal policy. Okay, so the optimal choice is not a single value of CT, it's a complete set of CT going into infinity. Okay, it's a plan. It's an optimal policy. So all these words are used interchangeably in modern macroeconomics. An optimal policy, it's a plan. It's a solution for the optimal consumption conditioned on the state in period t. That's the way of characterizing it. Okay? So I can't just choose an arbitrary function, because otherwise I just choose infinite consumption every period. It has to be constrained. It's constrained by two things. One is the dynamics of the capital stock. Okay, and here it is. I've divided by LT now. Forget the NT. LT equals NT. And basically the capital stock per capita evolves as a race between two things. One is the investment rate, the net investment rate, and the depreciation that I'm facing. Okay? And there may be a slight typo right here. I'll fix that. There should be a, no, it's there. This is fine. So you divide LT into KT, you get minus delta times little kt, and then you just rearrange it, you get that beautiful condition on the left. So basically the dynamics of the capital stock is the centerpiece. That is the resource constraint. That's the budget constraint, if you like. The central planner doesn't pay money. The central planner just plans, but the central planner can't beat the resource constraint. It's not God, okay? Can't just create capital out of nowhere. It's got to follow the capital. And the capital obeys this equation, this differential equation. So it's a race between how much I produce and how much I consume and how much I need, not just to replace depreciated capital, but to replace the capital per capita that gets lost when I have more capita, when I have more people. Okay, so again, if you understood the solo model, this is cake. Okay, and the second restriction, you've got this restriction and this is if you like, this is a sequence of constraints. It's a budget constraint in every period. You cannot break this in any period. So it's complicated. You can't use Lagrange on this. Okay, so if you hate Lagrange, you're really going to hate this. But, just grin and bear it, because education is painful. You're investing in your future. You're investing in ways to understand the world. Okay? The second condition we need to worry about is the initial condition for the capital stock. You're born with it. Angola gets K0 to start with. Sorry, you cannot, this model does not allow you to parachute in machines to Angola. Maybe they could afford it now with oil prices, but they can't do it. It's out of bounds. So you have to accept K0. So if you're South Korea, you got a different initial condition than China, and you got a different initial condition than North Korea. Okay, so you can imagine the different implications of the Ramsey model, even if everyone has the same utility function. Okay? So now let's get to the meat of the matter. I have to define the analog to the Lagrange function in static analysis, and it's called the Hamiltonian. Like, if you know who Alexander Hamilton is, it's a nice mnemonic, has nothing to do with him, but it is called the Hamiltonian function. Okay, it is the analog. It is also a real valued function that we're going to play with, take derivatives of, set them equal to 0, etc. It looks like a Lagrange function, but you can see there's a slight difference. It's actually defined for a point in time. Okay, so it has to be, this thing is true for all t. Also t equals big, big, big. Okay, the whole sequence. So it's the Hamiltonian function is kind of like the lump of clay that we have to play with when we start to carve out the correct optimal behavior. And we have to, basically, we know, and that's the cookbook, that we know that there's certain conditions on optimal behavior which have implications for the Hamiltonian, the derivatives of the Hamiltonian function. So just like the Lagrange, we have to play with this Hamiltonian function. I'm going to define the analog to the Lagrange multiplier. I'm going to call it the co-state variable. Okay, that's just what I'm going to call it. Okay, and it's something that is not restricted to the past. It actually can jump. Okay? The state variable cannot jump. And we only have one state variable in this problem, and that's the capital stock per capita. That's the only thing the central planner she can only control one thing. She can control, over time, the capital stock per capita by investing more or less. That's all she can do. Okay? So this is an easy problem. If you like this kind of stuff, if you like this, maybe you should do more of this. Take the growth course, take other courses, but this is just like putting the tool in your hand, letting you play with it. Okay? So at the optimum, this co-state variable has an interpretation in this problem. It is the value of relaxing the constraint at the optimum. If you remember Lagrange theory, the Lagrange approach said, If I'm on the budget constraint, if I give you an extra euro, what is it worth to you in terms of utility? If you're choosing the right thing all the way down the list of choices, that's the interpretation of the Lagrange multiplier. It's the same with the co-state variable. It is like, some people even call it the Lagrange multiplier, but it is a function of time. It's not just for one variable, it's for this variable from 0 to infinity. And think of it as the value in present value terms of giving the agent, this planner, a little bit more capital in any arbitrary period. We can't do that because it's out of bounds, but if I could, how much would it be worth to the central planner? The marginal valuation of a little bit of capital given that I'm doing the right thing. This is a deep concept. We call this a shadow value, a shadow price to the central planner of additional capital. It's out of bounds, can't do it, but if I could, what would it be worth to me? What would I be willing to pay as a central planner to get a little more capital into period T? That's what this mu, which will soon become a lambda, okay, is. So mu is the present value at T0, okay? So it's, again, the cool thing about these problems is it's about time. So we always have to think about time, and time only goes in one direction. We can't go backwards. Okay, so from period 0, we're thinking about the valuation of extra capital in every period of time between 0 and infinity. And that, if we do the right thing as a social planner, that mu has to have a certain behavior. Okay, because it's changing over time, and maybe we want it to change in the right way. That's the idea. So think of this as a function of time. It's in present value terms. So that means once I'm the central planner, I've chosen my problem, and then I let the economy run into the future, I can still think about this mu t, but mu t doesn't have much meaning anymore because by the time I get to period t, I'm actually have a different valuation of time than I did in period 0. So for convenience, and you're free to do this, we can redefine the Lagrange multiplier, or the co-state variable, in the following way. We're going to define lambda as the exponentiated value in time of mu t at time t from the perspective of the central planner in time 0. So this is called the current value of the multiplier. So that means I can go into real time and actually look at how the shadow value of capital is evolving in period t to the central planner. Okay, so this may not make sense to you now, but it will make sense in a few minutes. I'm going to actually take you through this derivation twice. Okay, but it's incredibly important because what's happening is basically the central planner is not only choosing savings, it has to choose savings in the dynamically correct way. So if the shadow value of capital is high in one period, it should be high in the successive periods. Otherwise, you could actually move investment around and probably make yourself better off. So it's kind of an arbitrage argument. A lot of people call this the arbitrage justification of this approach. Okay, now again, I'm trying to entertain you, but this is hard. But you see, once I've done this, I've actually got the same e to the minus theta t on both of these expressions, so I can factor that out. That's useful. Okay, because that means what's going to matter is basically the behavior of this function in its first derivative in comparison to this shadow value of capital. That's giving you a hint for the solution. Okay? So think of this Hamiltonian as our helping hand to help us solve these rather difficult questions. And we're going to use that form. So if you had to do this in an exam, you'd want to write down this form. Okay? Just to make your life easier, because it's easier to take those derivatives that you're going to have to take in the future. So I promised you a cookbook. And again, this is the hardest, formally, probably the hardest stuff we'll do, but it has a very high social product, or marginal social, because you'll spread this in your intuition into future generations, but also because it'll help you understand economics. So I'm going to use the cookbook approach. So there are 3 cookbook rules for doing this right. It's called the maximum principle. Just like Lagrange, you have this principle for setting the derivatives of the control variables or the choice variables, and Lagrange equals 0. And those are first order conditions. We have a similar set of conditions that's called the maximum principle. Okay, so here they are, and I'm going to apply them to our problem, and then we're going to take a break, think about it, and then we're going to come back and do it again. The first rule is like Lagrange. You set the derivative of the Hamiltonian with respect to every control variable you have at your planner's disposal equal to 0 at every t. Remember, this is not a single choice variable. And I say this again because a lot of people who take this course will write on the final that they're choosing a single thing. That's not right. You're choosing a function, and this is a characterization of the function. So at every point in time, the derivative of the Hamiltonian with respect to the control variable has to be equal to 0. Okay? So I'm going to take a break for a second. Now, you may not believe that man walked on the moon, but if you do, the way they got the rocket out there was using this type of theory. Okay, so dynamic programming was the way they did it. Okay, because it's not enough just to get the rocket in the air, you have to keep adjusting it as the conditions change. And of course, in that world, things are not certain. You know, something could happen, you have to change the course, maybe some weather conditions as the rocket's going. So this is called dynamic optimization. Okay, so basically, you're choosing this function of time. You're differentiating this function of time with respect to your control variable at each time. So that's one of the conditions. That's the second one, is the one that involves the dynamic optimization. So the valuation of the constraint has to also evolve in a certain way. Okay, so if you're doing the right thing, it's not enough just to do number one, but you also have to do number two. Basically, the co-state variable has to move in a certain way over time. Otherwise, you're not behaving optimally. Okay, so the number one sounds like static. Static in every period of time, but it's not enough. You have to make sure that the valuation of the constraint at every instant of time is changing in a certain way, and that's the second condition. The derivative of the Hamiltonian with respect to the state variable, which you cannot control directly, you can only control it indirectly, has to be equal to the negative of the derivative of the Hamiltonian with respect to the co-state variable with respect to time. Okay? And we'll take you through an example. We'll take you through this example, the Ramsey problem, and you'll see exactly what that means. Okay, so you're choosing the control variable, and you're also implicitly choosing the state variable to make sure that it obeys its marginal valuation as you move through time. Okay, that's kind of the intuition of what we're doing. And the final thing is what I call the cake-eating condition. Okay, so again, even if you do number one and number two right, and you think you're going to the moon, you may actually wind up somewhere far away. You may be obeying the first order conditions along the way, but the terminal condition may be wrong. Okay, so you obeyed all the rules that the NASA guys wrote down, and you end up on Mars. Okay, so you have to make sure that the final resting point is the right place. And in this problem has nothing to do with outer space, it has to do with eating the cake. So if you save a lot of capital, what good is it to do to have lots of beautiful lecture halls like this if we never use them? So in some sense, we have to make sure that we actually get something out of what we've saved up to. So it kind of sounds a little bit like dynamic efficiency. Okay, we have to make sure that we eat the cake. It doesn't make sense to keep putting cake in the refrigerator, and even if it's really good cake and it doesn't depreciate very much, you might have this refrigerator full of cake and you're saying, why am I doing this, right? I could make myself better off by saving less cake and just eating it. So that's the last condition, is just to make sure that we don't overdo it. Okay, and you'll see why in a second. It's very intriguing. It's an intriguing problem. You can imagine worlds, you can imagine an economy where the central planner is, incredibly rigorous. People are saving and they're fulfilling all the other conditions, but at the end of 500 years they have, pyramids that no one uses. Okay? That's one way of thinking about this. Or machine tools that nobody uses. Okay, so it's like you want to prevent over-investment in this particular application. But in general, it's a problem. You have to make sure that the valuation of the state variable at infinity is not such that you could actually change it without making anybody less well off and actually make everyone better off. So it's a little bit like dynamic efficiency. Okay, so take those three principles and apply them to our problem. First one is set the derivative of the Hamiltonian with respect to each control variable equal to 0 at every point in time. Okay? The second was set the derivative of the Hamiltonian with respect to the state variable to the negative of the derivative of the Hamiltonian with respect to the derivative of the co-state variable with respect to time. And then this transversality condition. So I'm going to apply that to our problem. I'm just going to write the math down, and I'm going to take you through it, and I'm going to show you why the intuition is really amazing. So there is intuition to this. It's not just playing with math. The central planner does the right thing. Okay? So the first condition is setting the Hamiltonian, which we already wrote down, differentiating it with respect to c, t at any point in time. That thing has to be equal to 0. Now if you do that literally with my problem, what do you get? You get u prime evaluated at ct, because you're differentiating with respect to ct, is equal to lambda t. Now remember, lambda t was the value of, in utility terms, at point t, at period t, of relaxing the resource constraint just a teeny weeny bit. So if you do it right, the value of relaxing at any point in time in t should be exactly equal to the marginal utility of consumption. So literally, you should be indifferent between either, at any point in time, between eating the capital and reinvesting it. And the value of reinvesting it is exactly equal to lambda. Okay? Now we're gonna actually push this even farther. We're gonna get rid of lambda. But first we have to do the rest of the conditions. This is a simple problem. We have one control variable, ct, and we have one state variable, little kt. So this is like a baby version of any sort of complex problem you might imagine. The second condition involves the derivative of the Hamiltonian with respect to kt and putting that equal to the derivative of the co-state variable with respect to time with a negative sign in front of it. Okay, so we have to remind ourselves what mu is. Mu is this present value of the relaxation of the restraint in period t, discounted to the present. So we need to insert what we said mu was. Mu t was equal to the exploded version of that from some initial period. So you would basically insert lambda t times e raised to the minus delta t. That's the discounted version of lambda. Lambda is the current value, and to get it back into present value terms, you'd have to discount it by theta and use that in this exponential discounting function. So you just plug that in here and take the derivative with respect to time. So now you have to remind yourself the wonderful characteristics of Euler's constant raised to a power. Okay? So again, Euler's constant is raised to the power minus theta t. So the derivative of that thing with respect to t is equal to the change of the co-state variable in period t discounted to the present, plus what? It's plus theta times lambda t times e to the minus theta t. That's applying the product rule and the fact that when you differentiate e to the minus theta t, you get theta back with respect to t, okay? So this thing looks very complicated. Forget that. Take this, and you can simplify it because we know what this is. This mu t is equal to e raised to the minus theta t times lambda t. So lambda t, e theta t cancels on both sides. So you have this wonderfully simple, elegant expression at the end, and we divide through by lambda t on both sides, and you can see what this first order condition with respect to the state variable actually implies. It says that the marginal product of capital has to behave in such a way that it's taking account of the growth rate of population. That's the old Solo model rule, the Phelps rule. Delta is the depreciation rate. The discounting of the social planner, plus the rate of change of that very co-state variable. So the rate of change of the co-state variable is the marginal, like the rate of return on the state variable that we have at time t. It's like a capital gain or a capital loss. So lambda dot divided by lambda is like the rate of change of the valuation to the central planner of this capital. So if the central planner does it right, that condition also has to hold. So this is different from what we had in Solow. In Solow, we thought about the Phelps problem. You just want to maximize steady state consumption per capita, and this was gone. This is a statement about how we get there. Okay? So we already know what lambda is. Lambda is the marginal utility of consumption. So when lambda is rising, what does that mean consumption is doing? If the marginal utility of consumption is rising, consumption must be going down. Right? Because we're getting hungrier and hungrier at the margin, we really like it. Okay? Lambda will be falling if our consumption is rising per capita, because the second derivative is negative. Okay, so so basically Ramsey is telling us we have to pay attention to that. People, if you move consumption real fast, it's going to make people really hurt, and it's going to make people hurt who are probably, getting more weight today because they're showing up earlier in life. Even though we have altruism with respect to all, it's the early consumption that gets higher valuation. Okay, so we're going to come back, we're going to play with that. That's a very interesting, that is like a lot of people use this in finance. This is like a finance valuation equation. It's a way of valuing an asset which we would call capital. Okay, it's basically a function of things like the marginal productivity of the capital as well as the opportunity costs of using it. And of course, it's depreciation. The last condition is this cake-eating condition. Okay, applied to this problem, it basically says, as we go to the limit, the valuation of a piece of capital into the future, valued in t0, has to be 0. Okay, so again, this is capital per capita at any period t. So t equals infinity is a long way away. What is that worth to me? It's worth mu, and mu is the present value of something I get in period t. And if I plug in the expression for mu t, it's the discounted value of the current value Lagrange multiplier. So I'm basically making sure that capital does not increase at a rate faster than the rate of margin utility is changing. I want that thing to go to 0. I want to make sure that I can't just eat the capital in the far future and make myself better today. That would mean that I didn't do the job right. I didn't optimize utility. Okay, so it's kind of an intuitive argument why this has to hold. This is the cake-eating condition in these problems. So we can write this out, and I try to do this in words again. Think of the first condition. Again, this is a very simple problem, and that's why we can use the phase diagram. The phase diagram has two variables. It has C and K. Okay, so I'll do that in a second. But already verbally we have some interesting insights. We understand that the marginal utility of consumption is equal to its resource cost, opportunity cost. Okay, so I could, again, the central planner could just say, okay, I'm going to give you some extra consumption, and we're not going to save as much. Okay. Now, if the central planner is doing it the right way, she would actually be indifferent between that choice. Because if I take from the investment and give it to you, you're happier, but I'm making other people less happy. I'm making future people less happy. So that trade-off, if you do it correctly, should make the planner indifferent between the two. So that's how we're going to characterize the path, implicitly making consumption a function of the marginal valuation of capital. Okay, so that's kind of getting us in the right mood for the rest of the second one says the marginal product of capital is somehow related to this stuff, population growth. Okay, because again, the higher the population growth, the more I'm going to have to keep reinvesting to equip these new people, and therefore marginal product of capital will be lower. Remember, marginal product of capital is also a concave, is a negative function of k. The production function is concave in k. I also have the subjective discount. So the central planner is very impatient, high theta. That means it's also going to hold back on investment and have lots of people consuming early on because she's impatient. If she's real patient, like Ramsey said, theta will be equal to 0. Okay? Of course, that is a problem. We can make it really slightly positive. And you can see that they'll have much more capital because people will be very patient. They'll accumulate more relatively quickly. Okay, and again, the transitality condition, it has this crazy name, transversality condition. It's like when you transverse time, the infinite future, what happens? It's like, it's like priests debating how many angels are on the head of a pin or something. A lot of people don't think it's relevant, but in fact, you can imagine economies like getting it completely wrong, even though they actually, people seem to be, happy and indifferent between different choices of consumption between today and tomorrow. Maybe on the path, they're just accumulating too much. We want to rule that out. Again, we're interested in the theoretical construct of the social optimum. The planner is trying to do the best for her people. Again, everything else is daneben. It's just, you missed it. You didn't get it. And that's kind of what's interesting about this, this normative approach to growth theory, this normative approach to a lot of problems that involve time. Okay, so we have CT, lambda t, and little kt. Those are our, now lambda, I've never seen a lambda, right? That's why a lot of people think economists are nuts, right? But we need the lambda to understand the C. So think of lambda as like a Hilfsmittel, it's like a crutch to get us there, and then we throw it away. So we can do that here, because lambda has a very simple expression. It's just the marginal utility of consumption. If I do the right thing, lambda is it, so I can get rid of it. I can substitute it completely away. I can eliminate it from the problem. Then I have a problem. I have a characterization solution in two observable variables: consumption per capita and capital per capita. Right? So I'm golden. So compactly written. Okay. First order condition with respect to the Hamiltonian, now written for every t. Again, this is not just for one period. This is for all of time. Every instant we have to be obeying these rules to do the right thing. Second one is the evolution of lambda, and lambda is the marginal product. So we're actually making a statement about the evolution of the marginal product, the marginal utility of consumption. Okay, that's why the second prime appears there. It's the second derivative of consumption. So if you had linear utility, the second derivative would be 0. Linear utility would mean that I don't care whether I consume today or tomorrow. It's the same in terms of, it doesn't, if I consume more or less, the marginal utility doesn't change. That's really what I'm saying, okay? So that's not what we observe. One of the most robust facts about people is they like to smooth consumption. And Ramsey got that. Robert Hall got that. Milton Friedman got that. We all get that. There are some qualifications. Some people can't use capital markets, but people want to have a stable existence. That's kind of what this is trying to capture. So if I do that, and I just substitute the derivative of lambda with respect to time, I get this interesting object. It looks like the coefficient of risk aversion, the coefficient of absolute risk aversion. But that's not, we don't have any risk in this model, so you can't, but it is actually that. It's the inverse of the curvature measure of the utility function. Okay, and we'll get to that in a second. So basically my desire to smooth consumption depends on how much I hate to move my consumption very fast. Right? So a lot of people are really kind of rigid, and some people are really flexible. So if you're flexible, your marginal utility of consumption doesn't change very much. It changes a little bit. And if you're just really just obsessed with eating, 2 pieces of bread for breakfast and blah, 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 then basically you're not going to react very much. You're going to have a lot of disutility of moving consumption. So the central planner knows that, knows you, and will actually embody that into the optimal plan. So this is a characterization of the optimal plan. Note, these are all things we can observe. So if we want, we can actually try to look at the data and see if things vaguely appear to resemble this in the long run. We could do that. We could also just theoretically track out the path, the dynamic path of these variables. It's a system of differential equations, 2 differential equations of first order. So they're nonlinear, but it's not the end of the world. And physicists showed us how to do this. We don't have to even solve it. We just draw a picture. And that's all I'm going to ask you to do. Because I believe in pictures. I believe in the power of visualization. Okay? If you really want to be a great economist, you probably have to do more than that. But we can all agree, if it's not an oversimplification, visualization can be a great help. Okay, so I'm going I'm going to take this and I'm going to plot it in a second. Okay? You can see that I've actually done something. Look what I did. I just divided by CT on both sides. I can do that. CT is never 0. Okay, so what do I have on the left-hand side? I have the rate of change of consumption. Okay, for those of you who didn't catch it, you were probably reading your email or something. I went from here to here, divided by CT. So now I've got the rate of change of consumption on the left-hand side, and I've got the marginal product of capital minus delta is the real interest rate in a decentralized economy. We don't have any interest rates in this economy because the central planner is doing all of the puppeteering. But I've got N, and I've got the private discount rate, or the social planner's private personal discount rate. And what is this object? This object is a positive number because it's minus times U double prime, which is negative, and U prime is positive. This thing is kind of like the elasticity of intertemporal substitution. It's not just kind of like, it is. It is a reflection of how ready we are to trade off consumption today as manipulated people in this central planner's problem between consumption today and the consumption in the future. What is the relative trade-off in terms of the ratio of consumption today versus consumption tomorrow if I change the relative price, okay, of consumption today versus consumption tomorrow? You don't see any prices here, but you implicitly do. The resource cost of moving consumption to the future is the productivity of capital tomorrow versus my impatience today, effectively. Okay? So that's kind of why this substitution, we're going to use sigma to describe this. And sigma is an interesting object. If sigma is infinite, okay, that means that basically I don't care, okay? I'm ready to move consumption back and forth at a whatever. And if 0, it means I really have rigid consumption tastes. I want to consume the same amount basically, regardless of what the relative costs and benefits are. Okay, and the central planner is looking at all this in the eye and doing it. Okay, so now I'm going to take back, this is hard, I'm going to take back, I'm going to repeat everything for you, and then we're going to do the picture. I still have 10 minutes. Okay, so the problem, the central planner is choosing a function of time. And again, I do this like this just to remind you, and we write it for convenience like that. I don't want anyone to forget this is a function. And later on when you do more advanced macroeconomics, you do it naturally. Think about this naturally. Because macroeconomics is about time. You know, that's the advantage we have over microeconomics. We actually think a lot about time. Okay, I shouldn't say that too. My neighbors may come get me. But it's an interesting fact that we think a lot about the opportunity costs and the benefits of doing things in temporal sequence. Okay? The cookbook, lots of derivatives. And again, it's a function. The Hamilton function, the Hamiltonian function, is a function evaluated at each point in time. It doesn't have any integrals in it. It has the integrand, and it has the constraint at every point in time. Gesundheit. So that's the important thing to you remember is it's just a cookbook for you. But believe me, a lot of people in engineering use this, and they use it like a cookbook. They don't care. They don't care about the bells and whistles and the mathematics. It's a tool for us. Okay? And if you apply that, you get these 3 principles. You get 3 sets of conditions. The first one is very important. It says that you set consumption such that the planner is indifferent between the immediate gratification today of consumption, which is the left-hand side, and the future benefit, which is the value of having that stuff in the machine producing consumption in the next instant. Okay? So it's the shadow value of a helicopter drop of capital into this economy. So again, economists are free to do this. We can assume that this could happen, and what would it be worth to us? Because if it's worth a lot, maybe we should do it. Okay? Maybe we should consider it. And people in applied economics often compute shadow values of a lot of things that can't be changed. What is the shadow value of getting the Nord-Süd Trasse finished? Think about that. All the wind power we're collecting in the North Sea, and what are we doing with it? I think it's just going nowhere. These things are turning, generating lots of electricity, but the social planner in Germany didn't get it right, didn't build the power lines. What is the shadow value to the German economy of having those power lines in place right now? We know that it's going to take a lot of investment. We can still calculate the value to the German economy right now of having it right there. That's what shadow value is about. Okay, so keep that in mind. This is a very important idea. So we have this trick. The trick is relabeling the present value multiplier, which we call mu, in terms of the current value lambda, because then we can track lambda as we go through time. We don't have to track the exponential function. You'll see this when you do the problem. And then you have to remember the rules of differentiation. So I've written this down for you as an extra, little helping hand to show how we get there. Okay, because the second rule applies to the mu. It doesn't apply to the lambda. It applies to the mu. So you have to plug in the value of mu, which involves the lambda, which we care about and helps us think about it. And again, you have to remember the rules of differentiation. Product rule, differentiation of exponential functions, everything with respect to time. Remember, the planner is choosing a function as a function of time. It's like this string of consumption choices from 0 to infinity. And we're trying to characterize that under the conditions of optimal behavior. Okay, so now if you let me do this, I'm going to now go from here, and I'm going to define that expression as sigma. Sigma is this intertemporal elasticity of substitution, or elasticity of intertemporal substitution. Okay, you can see why it's important. The planner cares about these people, and these people are facing a productivity of capital, which is pulling them to do more savings, but it also has to consider the fact that the capital is going to depreciate. So even if they invest a lot, it's going to waste away. Maybe the depreciation rate is very high. Could be. Maybe the planner is very impatient. The theta might be very high. Or a lot of new population, larger populations forthcoming, which mean that they dilute the value of capital. So if you save it, what's it worth to you in the future? Not a lot if you're reproducing like crazy. Okay? So again, this sounds very cynical, but it's true that countries that have very high population growth rates have problems growing. And we don't want to say it's exogenous, but it may be part of some larger endogenous problem that the central planner might have to care about. Because in poor countries, people don't survive. Families react to that by having lots of children. Okay, it's a fact. And it's an impediment to growth. You can see it here. The central planner has problems dealing with this. The central planner, seeing all these people come, will invest less optimally. Okay? Now this is called Ramsey's two-variable dynamic system. Okay, and that's what I want you to remember from today. So we're like 7 minutes out from finishing, and you can have lunch. This is basically the action of the model. We have a rate of change of consumption, which everyone can deal with, right? It's kind of like the rate of change of your material well-being, because you don't get utility from investment, you get utility from consumption, and you get it in a way that's kind of not linear. So if you take it all today, you're going to regret it because you didn't take more tomorrow. Okay? The second equation is a state equation. The state is capital per capita. Okay? So that was given to us at the beginning. That was our resource constraint, effectively. It just says what the central planner cannot beat this. The central planner has to accept this as a given. Okay? But the central planner can affect K at every point in time by doing a lot of investment in the previous periods. Okay, so a state variable means literally you cannot change it in point t, but if you do something in t plus epsilon, it will be different. That's what this is about. So even if you do discrete time models, you have to worry about this, because if you invest today, you're not going to get anything to produce with until tomorrow. Quarterly model, weekly model, monthly model, whatever. State variable is capital in this problem. We also define the elasticity of intertemporal substitution. Okay, and again, for those of you who are paying attention, it is related to risk aversion. And the way we've defined it here, we've divided by CT on both sides, so that's why it's a relative risk aversion coefficient, inverted. but you could also think of it as being, if you just take CT on the left-hand side, you would relate it to the absolute curvature or curvature measure of the utility function. Those of you who like finance will love this, because this is kind of, even though we don't have risk in this model, it's in the background. The reason why people avoid risk is for the same reason. They don't like fluctuating consumption. Right? They buy insurance to keep, if your house burns down, kind of tough, no house. So you buy insurance. You want a smooth consumption over states of the world. Same thing here with respect to time. So we'll finish with the Keynes-Ramsey rule. Now Keynes saw this, was completely amazed, and actually uttered something to Ramsey, and Ramsey thanks him in the paper. Okay, so apparently there's some dynamic interactions going on here. If you look at this carefully, this says basically the model has a prediction about the rate of change of consumption. Consumption is growing in economies where capital is very productive relative to the opportunity costs. The planner will consider that directly, and it will consider it, weighting it by the intertemporal substitution elasticity. So if people are really kind of rigid, the incentives may not have such an effect on the growth rate of consumption, but if the central planner is doing the right thing, consumption will rise per capita if the marginal product of investment warrants it relative to population growth, impatience, and depreciation. Okay? Similarly, you can imagine, again, Angela Merkel, von der Substanz leben, right? Shrinking C, it's possible to explain. You could imagine a situation where you realize, we have new conditions now. We're just going to eat this capital. I'm going to start living in my office. There might be some reason that justifies that. And that would be a case where this expression is inverted. The marginal product of capital is lower, and population growth is higher, depreciation is higher, et cetera, and you start living for today and less for tomorrow. Okay, so this is a really important prediction. It generally says that the rate of growth of consumption is related to things like the fundamentals of economic growth. So think of China, for example. It's a fact that China's per capita consumption is growing. It's growing very fast. And we think it's kind of related to these incentives, and you might think China has a central planner. Actually, it doesn't, but it has something close to it. They have planning. So, it does kind of make sense to have a gradient of consumption with respect to time that's higher than it is in Germany. In Germany, consumption looks like this. It's growing a little bit more than it did before, but for 10 years after the Hartz reforms, it was like this. Okay, so one interpretation of that might be expected low future growth. Okay, different interpretation. Again, it's more of a rationalization. A true interpretation would require more data. Okay, but it's something economists do. So the Keynes-Ramsey rule says that consumption per capita increases or remains constant or decreases depending on whether the marginal product of capital per capita, net of population growth and depreciation, exceeds less than or equal or less than the rate of time preference of the social planner. We're still talking about the social planner's best shot. We haven't talked about the private solution yet. That's next week. The interesting thing is, how close can we get to this theoretical construct? Okay? So it's not just the incentives of the central planner, the marginal productivity of capital relative to this stuff. It's also how willing the central planner is to respect the wishes of the population, which she will, and how desirous the population is to shift consumption in response to those incentives. Okay, so you can imagine a case where if people are very rigid, sigma is very low, possibly zero, and the central planner says C dot divided by C is equal to 0. We're just going to attain our consumption. We're just going to be very, very happy having very smooth consumption and non-changing consumption over time. Okay, so what I'd like to do next time is to discuss the following. What happens when C dot equals 0? What happens when C dot divided by C equals 0? What happens when we reach some sort of fictitious steady state? Okay, can we discuss that? Well, we sure can. If you look at the two differential equations, you can imagine this equals 0 and that equals 0. No more dots. We've reached a steady state. Okay? And what do we have? We have two equations in C and little k. Two equations and two unknowns. Sounds like a graph. Sounds like a phase diagram. The cool thing about the phase diagram is we can look outside the steady state and ask how these things are changing. And that's what's really neat. And that's why we do it. Because we don't have to commit to any function. We don't have to commit to writing down a utility function. We just has to fulfill some minimum requirements. We don't have to write down a production function. It just has to meet some minimal requirements. And we can actually write down a system of dynamics. And I'll just show you what it looks like to give you a preview. It's going to look like something like this. Beautiful picture. Beautiful. And with that, we're going to describe the way we reach the green dot. So I won't post this diagram. I just want you to think about it. And have a nice week. I'll see you next week.